All right, let's get right into it. We see it every single day. It gives us warmth, it gives us light, it gives us life. But what is the sun really? In this explainer, we're going to take a journey from its wild, turbulent surface right down to its unimaginable core to really understand the powerhouse sitting at the center of our solar system.
From way over here on Earth, the sun can look like this serene, perfect, unchanging ball of light in the sky. But that peaceful look, it's totally deceiving. It's actually a place of constant, violent change driven by forces that had scientists completely stumped for centuries. So, what's really going on in there?
Well, for starters, let's just talk about sheer scale. You could fit 1.3 million planets the size of Earth inside the sun. I mean, that is just mind-bogglingly huge. It contains more than 99% of all the mass in our entire solar system. And get this, here's the first big idea we need to wrap our heads around. The sun has no solid surface. None. It is not a burning rock. It's a massive sphere of gas that's so incredibly hot, the atoms themselves have been ripped apart, stripped of their electrons. This supercharged, electrically conductive state of matter, yeah, that's called plasma. So, this brings us to the central puzzle, the big one, that stumps some of the greatest minds in science for ages. We know from looking at rocks and fossils here on Earth that the sun has been shining steadily for at least 4.5 billion years. But how? What could possibly fuel something for that long? The early theories just didn't work. I mean, if the sun were made of something like coal and just burning like a normal fire, it would have burned out in just a few thousand years. Then there was another really clever idea that gravity was slowly squeezing the sun, converting that gravitational energy into heat. But even that model could only power the sun for about 100 million years. A long time for sure, but nowhere near the billions of years required. Turns out the answer wasn't found by trying to figure out the fuel source. Nope. It came from observing these strange features on the sun's visible surface. These were the first real clues that something way more complex than simple burning was going on. And the most obvious of these clues are sunspots. Now, they look dark, but don't let that fool you. They're still unbelievably hot. They only look dark because they're being compared to the even hotter plasma all around them. And here's the crucial discovery. These spots are areas where intense, powerful magnetic fields are poking right through the surface. So how do these magnetic fields get so intense? Well, because the sun is a giant ball of plasma, it doesn't spin like a solid rock. The equator actually spins faster, making a full rotation in about 25 days, while the poles kind of lag behind, taking more than 30 days. This differential rotation grabs onto the sun's magnetic field lines and just twists them up like giant rubber bands. And all of this tangling and untangling creates a pretty predictable rhythm. The magnetic mess builds up over time, leading to a peak of activity we call solar maximum. Lots of sunspots, lots of solar storms. Then the field kind of resets itself, and things get quiet during solar minimum. This whole thing just repeats over and over again in a cycle that lasts about 11 years. Okay, so we've got magnetism driving all the action on the surface. But to find the sun's real energy source, we have to go deeper, a lot deeper. So let's take a tour through the sun's layers, starting from the outside and making our way right to the core. All right, starting from the very outside, you've got the sun's atmosphere, the superfaint corona and the reddish chromosphere. The part we actually see from Earth, the surface, is called the photosphere. Go deeper and you hit the convective zone, where hot plasma churns and boils, kind of like a giant pot of oatmeal. Below that is the radiative zone, which is so ridiculously dense that a single photon of light can take more than 100,000 years to get through it. And finally, right at the very center, you have the core, the engine room. But wait, before we get to the core, check this out. It's kind of nuts. As you move away from the visible surface, the temperature doesn't drop like you'd expect. It skyrockets. The corona, the sun's outermost layer, is hundreds of times hotter than the surface below it. This is one of the biggest unsolved mysteries in solar physics, and it tells us some really powerful, non-obvious stuff is going on to heat the sun's atmosphere. Okay, we've made it. The center, 15 million degrees, pressure that's over 250 billion times what we feel on Earth. Right here, in the sun's core, we finally find the answer to that billion-year-old mystery. And the key to this whole puzzle didn't even come from an astronomer. It came from Albert Einstein. His famous and actually pretty simple equation revealed that mass and energy are really just two sides of the same coin. Matter itself can be converted into absolutely immense amounts of energy. So here's the punchline. The sun doesn't burn like a campfire, it shines through a process called nuclear fusion. In the insane conditions of the core, the simplest element in the universe, hydrogen, is violently smashed together to create the next element up the ladder, helium. This happens through something called the proton-proton chain. Basically, it's a three-step reaction where protons, which are really just hydrogen nuclei, are forced together. Step by step, they build up until, pop, you've got a stable helium nucleus. The main thing to remember is that hydrogen goes in and helium comes out, with some protons left over to start the whole cycle again. Okay, and this is where Einstein's E equals mc squared really clicks into place. The final helium nucleus that gets created is actually a tiny bit, about 0.7%, less massive than the original hydrogen bits that went into making it. That lost mass didn't just vanish, it has been converted directly into pure energy. And the amount of stuff we're talking about here is just staggering. To shine as brightly as it does, the sun's core has to fuse about 600 million tons of hydrogen into helium every single second. And of that, about 4 million tons of matter is just annihilated, poof, and turned into pure energy every second. That is the secret to its long life.
Now, all of that incredible power doesn't just stay 93 million miles away. That energy and activity travels across the whole solar system, and it has very real effects right here at home. This whole thing is what we call space weather.
You see, the corona is so incredibly hot that the sun's gravity can't hang on to all of it. So there's this constant river of charged particles, mostly protons and electrons, that flows away from the sun in every direction. We call it the solar wind, and it blasts through the entire solar system at incredible speeds.
And when this solar wind reaches us, it creates one of the most beautiful sights in all of nature. Our planet's magnetic field acts like a shield, funneling those charged particles toward the north and south poles. As they slam into the atoms in our atmosphere, they make them light up, creating those spectacular light shows we know as the aurora.
But it's not always so gentle. During its active periods, those tangled magnetic fields can snap, unleashing explosive solar flares and launching billion-ton clouds of plasma out into space. We call those coronal mass ejections, or CMEs. And if a big one hits Earth head-on, it can overwhelm our magnetic field and cause huge problems for our modern tech-heavy society. So you end up with this incredible duality, right? The very same nuclear furnace that gives our planet life-giving energy can also unleash these powerful storms that threaten our entire way of life. It's a constant reminder that we live inside the dynamic, ever-changing atmosphere of a very active star. The question isn't if the next big storm will come, but when, and how well prepared we'll be when it does.